Last episode, we designed a crawler and pulled the whole web down. This episode, we design one special structure that lives inside that web: a social network. People are the nodes, friendships are the edges. One giant graph. Sounds simple, but the hard part is a feature you use every single day. You and this person, how many degrees apart? 100 million users, 5 billion edges. How do you answer that in a snap? Let's find out. First, do the math.
100 million users, 50 friends each, 5 billion relationships. A billion friend searches a month, 400 a second.
One key line. This graph does not fit on one machine. Remember it, because everything after this is forced by it. Degrees of separation, translated into an algorithm, is this: shortest path on an unweighted graph. That is BFS, breadth first search. Start from you and expand outward, layer by layer. 1 degree, 2 degrees, 3 degrees, until you hit the target. Here's the problem. The social graph is 6 degrees of separation.
To reach someone 6 hops out, BFS has to sweep half the graph. On a 200,000 person graph, it visited 100,000 nodes.
Scale that to 100 million users, and it's a disaster. One beautiful pivot. Don't search from just your end. Search from you and the target at the same time, and meet in the middle. Each side walks only half the distance. 3 hops.
Same 6 degrees of separation. One-way visits 100,000 nodes. Bidirectional visits only 111.
That's about 900 times fewer. And think about it. On a sharded graph, every node you visit is a network call across machines. Visit 900 times fewer nodes, and that's 900 times fewer network round trips. That is the real value of bidirectional BFS. But there's a landmine here. Celebrities. A normal person has 50 friends. A celebrity has 5 million followers.
The moment BFS expands into a celebrity, it has to cram 5 million neighbors into the frontier. 100,000 times the work.
The frontier and memory blow up on the spot. And celebrities also collapse distance.
10 million people all follow the same celebrity, and every pair of them becomes 2 hops apart.
But that's not actually close. The fix is exactly the same as the celebrity fan-out from the Twitter episode. The tail of the degree distribution has to be handled on its own. The average lies to you. The maximum is the one that crushes you. So how do you actually store this graph? One option: an adjacency matrix, 100 million by 100 million bits.
1.1 petabytes, and 99.9999% of it is zeros.
Absurd. You stored a whole petabyte of zeros.
An adjacency list stores only the edges that exist, 5 billion of them, 37 gigabytes, 30,000 times smaller.
A graph is sparse by nature, so you have to use an adjacency list. But 37 gigabytes, plus the indexes, still doesn't fit on one machine. Shard it.
A lookup service maps a person id to which machine it lives on.
Every BFS hop can cross machines. And graph partitioning is a genuinely hard problem. Friends clump together naturally, so when you try to cut cleanly, you can't. So where does AI touch this one? Friend recommendations. People you may know. The classic approach. Count common neighbors. The more friends the two of you share, the more you should be connected. This is called triangle closing.
Pure graph structure, no model. This is the workhorse behind people you may know.
So what does a GNN add? It learns a vector embedding for every person from the whole graph.
It captures structural signals beyond 2 hops and recommends the connections common neighbors miss.
One level up, GraphRag. Walk along the knowledge graph and feed the neighborhood to the large model. The 4 questions, plus the honest note.
Where it helps. A GNN learns whole graph embeddings for recommendations. GraphRag feeds graph neighborhoods to the LLM. where it replaces. The pure common neighbors rule gets replaced by learned structural similarity, where it changes things. One more layer of graph embeddings plus a vector index. Recommendation goes from counting triangles to comparing vectors.
And what can it change? Let me be honest. AI doesn't change the graph model, doesn't change bidirectional BFS, doesn't change supernode handling, doesn't change sharding. That's the skeleton. How many degrees apart the two of you are is still a job for BFS, not a job for the model. A GNN learns who should connect to whom, not who is how many hops from whom right now. Structure underneath, model on top. Before we wrap, a few pitfalls. 1. Using the wrong traversal. You only reach for Dijkstra on weighted shortest paths. Friendships are unweighted, so BFS is plenty. Don't use a sledgehammer to crack a nut. 2. Forgetting bidirectional. One-way BFS on a big graph is suicide. 3. Not special casing supernodes. One celebrity can drag down the entire search. 4. The adjacency matrix. Don't even think about it. 5. Graph partitioning is hard, so don't count on a perfect split. Accept the cross-machine hops and lean on caching and offline batch computation to cover you. Let me weld it into one sentence to close. A social network is a sparse graph plus bidirectional BFS plus supernode special casing plus sharding. Again, it's the parts from the last few episodes. Sharding, caching, lookup, queues. Bolted together. AI stands on top as the recommender. But the skeleton of how many degrees apart you are is a classic graph algorithm. Next problem. We design the key value store behind a search engine. Consistent hashing, sharding, replicas. See you then.